with the vectorization.
Alright, great. Even better. Alright, hello. So I'm Ben. So that was a great introduction. Thank you very much. So data parallel Haskell is all about nested data parallelism on shared memory multicore. DPH extends the work on Nestle to a more expressive language, in particular higher order functions and partial applications. So what I'm going to talk to you about is some of the issues we found when implementing these more expressive features on top of what Nestle gives you. The main thing was that our previous version of DPH used to break the asymptotic complexity of a class of programs. So you could have a program which was supposed to be linear, so order n, linear in terms of the data size, but when compiling with data parallel Haskell could turn it into quadratic, so n squared. So that was bad, and I'll show you how we fixed it. So it used to be bad, but not anymore. Alright, so here's the smallest example which actually demonstrates the problem. And it's fairly technical, so I'm going to try and explain this slowly. So this retrieve function takes, stand over here, this retrieve function takes two nested arrays. A nested array of characters and a nested array of indices. And look at the output here. So B is the first element from this array, and A is the 0th element from this array, B is the first element, and so on. So E is the second element from that array. See what's going on? So if we were to implement this in terms of DPH code, we'd have something like this. So this A type constructor is just short for array. And here's the code for it. Now, a difference between DPH and Nestle is that DPH allows Haskell-like higher order functions like zip width and map instead of the array comprehensions that Nestle uses. Now, in particular, I want to pay attention to this expression here. So map p index XSS. So the result of this expression has this type. So this expression is building an array of functions. It's building an array of 4 functions. And each of those functions captures this table in its closure. And then the function for this column, when you apply its last argument to 1, it gives b. And then apply the next argument to 0. So the second function in this array handles this column. So when you partially apply it to XXS, it captures CDE in its closure. And then when you apply the last argument 2, you get E, and so on. So we're talking about partial application and the fact that arrays are being captured in the closure of a partially applied function. Here, I should mention that the thing that makes this a nested parallel computation is that I've used parallel function map p as the worker of another parallel function. So map p is inside zip with p. Okay, so I'm going to show you how that code would be vectorized in DPH. So DPH, first of all, does a program transformation. It takes the source code and then vectorizes it, and then it runs the vectorized code with a back-end library of array primitives. Whoa. So here's the source code that we start with, and here's the vectorized code. And we'll step through how this works. Okay. The first step is I take this array of indices, and I just take the lengths. And then I take my array of lengths, and I'm going to apply this replicates operation to each of the elements of XSS. So see what's happening here is I'm replicating AB by 3, and then CDE by 1, and then FG by 2, and so on. And yeah. And I'm going to take the indices array and concatenate it. And then what I get here is each of these arrays is lined up with the corresponding index, and I'm going to use this thing called lifted indexing, which takes corresponding pairs of elements of these two arrays and then performs indexing. So I get the first element and then the 0th element and then so on. So this is all the elements that should be in my result, but I don't have the nesting structure that should be in the result. So the last step is to apply this unconcatenation. Sorry, this clicker is driving me crazy. Apply this unconcatenation function, which takes the original nesting structure of IS and then reapplies it to the elements which I've got, which gives me my final result. So that's the process where we would the DPH uses to evaluate the code in parallel. So each of these array primitives has a parallel implementation in our backend library. So I want to pay particular attention to this function here, replicates. So this replicates function essentially expresses the sharing between the XSS table, so the AB, and then the way I've applied it to every element in ISS. So move that up there, and then expand out the example code I was using. Now when I said sharing before, bring your attention back here. When I say map P index XSS, I'm building a partial application where the arrays in this table are being captured in the closure. Partial application implies sharing, because usually once I've partially applied a function, I want to use the partially applied result several times. So every time I have partial application, I have sharing, and then this replicates function sort of encapsulates that. Now, there's a problem with the array that was produced by replicates, in that I said partial application is all about sharing, but the array representation which Nestle uses, which we inherited from Nestle, cannot represent sharing. So if I have this array value, which was created by replicating an array which just had AB in it, and now I've got 3 copies of it, in the Nestle representation with its segment descriptor and data vector, the only way I can represent the logical value of this array is by physically copying all of the elements. This is the killer. So if you imagine a pathological function like this, here's my original function, and I'm going to apply it to 2 example arrays, both of the same length. The trouble is that if you were to evaluate this function retrieve in terms of the source program, assuming that the source program was just using, say, a pointer-based representation of arrays or nested lists, then in terms of the source program, the program would run linearly in the size of both arrays, 8 in this case. But then when we vectorize it, because our array representation can't represent sharing, we essentially copy the ABCDE table once for every element in the second array. So the whole runtime turns into quadratic in the size of the array, which is bad. So this wouldn't be a problem if we were using a pointer-based representation of nested arrays. So if we just had an array of pointers, which each point to smaller inner arrays, that wouldn't be a problem because pointers can represent sharing directly. Unfortunately, this is no good for parallelism. Naive pointer-based representations have very poor locality because you might have lots of little sub-arrays spread all over memory, and it's also hard to distribute across processors. So what we want in DPH, this is the gold standard of nested data parallelism, is to say, well, take my source program, suppose it was implemented in terms of pointer-based nested arrays. But when we vectorize it and run it with our system, we want it to have, first of all, the same asymptotic work complexity, but run in parallel and be faster than the sequential version. But this first point is the most important point. Alright, so what we did when faced with this problem is that we looked at the operators we had to implement and then just cast around for a different array representation. So here's the cipher signatures of the key operations that we have to implement to compile vectorized programs. And here are the complexities which the Nestle-style nested array representation gives us. And you can see that they're all worse than if we had used a pointer-based representation. In particular, say when I replicate a nested array, if I was using a pointer-based representation, that would run linearly in the size of the result. I'm talking about the length of the top level of nesting. But in the Nestle-style arrays, I can only replicate by deeply copying all the data. So the complexity is linear in the total number of elements in the array, not just the length of the top level of nesting. So most of the operations, the Nestle-style representation is worse. There are a couple where Nestle-style array representation is really good, namely concat and unconcat. Because if you remember the representation, we have a segment descriptor up the top which describes the subarrays, and then we have all the data elements down the bottom. To concat, you can just take off the segment descriptor and leave the elements behind. And this was a very seductive idea. It's like, isn't it so wonderful that concat and unconcat are order one in the Nestle-style representation? Unfortunately, it turns out that you don't actually need that when you compile vectorized code, because it turns out in the vectorized program, so here's the vectorized version of my example function. Every time we use concat and unconcat, we will also use another function, for instance, index L is lifted indexing, which has a higher complexity. So if index L is linear in the length of the result of concat, then concat doesn't need to be constant time because we only care about the complexity of the whole vectorized program. Okay, so we need a new array representation, and this is what we came up with. So it's got it's actually really simple. Simon, you're laughing. Okay, so at the top, we have the array that we want to represent. This is the logical value of the array that we want to represent. And at the bottom, we have the data in memory, so physical data in memory. So I'm going to keep all of the array data in just two blocks in memory. Imagine these are just data.vectors. So I'm going to define my logical array at the top based on the physical array at the bottom. So to do that, I only need to keep 3 extra vectors of values to tell me where my subarrays are inside my data. So I have a segment length field, which is the same as in Nestle. So the first of my segments, AB, has length 2, and the last one has length 1. And then I keep a vector which tells me which block, which physical block my segment comes from, and where it starts in that block. So that defines each of the physical segments that I have in memory. And then I have another vector at the top, the segment map, which tells me how I form the virtual the logical array from the physical data. So at the top I've got 0, 0, 0, which means I want 3 copies of the first segment. Okay? So it's only two extra fields above the Nestle-style array representation. Okay, so it's not that complicated. Okay. So once we have this representation, we have to go and find implementations for all of our operators that we care about, which give the correct complexity. And the main contribution of the paper is to give a reference implementation each of these operations, and then a justification for why they have to have the complexities that we say. Okay, so these were the complexities of old-style Nessel representation, and then new DPH. So we can do all the operations in the same asymptotic complexity as the pointer-based representation, except for indexing, when the result of the indexing is also a nested array. But it turns out in vectorized code you don't actually need this operation, because all of indexing operations in the source program get converted to Lifford indexing, and then we can implement Lifford indexing with the correct complexity. Okay, so we win. Yeah, and each of the operations that we present can also be implemented in parallel, which gives us the parallelism. There's more stuff in the paper, which I just summarized before. There are a couple of invariants that you need to have to maintain on this representation, but in particular, you can't have descriptors of physical segments that are not reachable from the top level segment. So for instance, we can't have an extra column here pointing to some segment, but that segment is not reachable from the logical description because that breaks the complexity of some other operators. But it's a fairly straightforward invariance. So skipping to the benchmarks, here's sparse matrix vector multiplication, and then this program doesn't actually use partial application, but it does something similar in that this vector argument, which is the dense vector it's going to multiply with the matrix, is reused for every application of this term function. So because I'm reusing this inner function which has a free variable multiple times, what used to happen is that the dense vector was copied for every row in the table. Not anymore. So here's the graph. So the red line is the old data parallel Haskell using Nessel style arrays. This is a log graph, by the way. The green line is a direct sequential implementation written with unboxed data vector library. And then the blue is our new arrays. So it's about 4 times slower for tedious engineering problems, like we haven't got everything unboxed and the array fusion needs some tweaking, but we're confident we can get that on par. So here's another example. We did a Barnes Hut gravitation simulation written in a more natural style than the Nessel one which was mentioned. So we use partial application, use higher order functions to our heart's content, what a Haskell programmer would write. The problem with this program was that, I'll back up, Barnes Hut runs by first creating you take all the points, which are the gravitational bodies, and you insert them into a quad tree to sort them, and then you calculate the acceleration on every point by using the quad tree. What used to happen is that the tree that you computed was captured in the closure of this inner lambda abstraction and then deeply copied for every body. So if there were 1 million bodies in the simulation, then the quad tree was copied 1 million times, which is bad. Not anymore. So here's the graph. So red is bad, using Nessel style arrays. Green is written with data vector, and it's the blue line which is the new array representation. And you can see it's got the correct asymptotic complexity. It's about 10 times slower than data vector in the limit, but once again that's just for some array fusion stuff and unboxing things that we haven't fixed yet. But I got a plan for that. Alright. Yeah, things that need to be fixed. I said that. Okay, thank you. Questions?